Today, we are going into some very abstract and bizarre things. The worksheet, the relativity worksheet, I'll be going over that on Monday. Um, so have it done by then. But today, I'm going to talk about, well, you can see right there, the nature of space in the multiverse. So that's fun. And this sounds like very science fictiony things, but well, there's basis for this stuff that could be true. So we're going to get into. But first, you have a question that will seem very obvious. Can you go faster than the speed of light? That's it. Answer the question. You probably said no, and the here's how I would phrase this question to be as accurate as possible, or phrase the answer. No, you cannot go faster than the speed of light through space. That's how I would answer that question. You cannot go faster than the speed of light through space. Now you might think, okay, so what? Well, the fact that I added that qualifier, if you could somehow not go through space, maybe go outside of space, then you could. Now, in order to talk about this, we have to talk about what even is space. This is a question I like to ask to people. Like, for example, when I did the astronomy class at Clayton Valley, this is actually one of the first warm-up questions I did, and it was just, what is space? What is space? What is it? And a lot of people will say that it's just nothing, right? It's when if you go out and you take away all the atoms, all of the subatomic particles, the light, all of that stuff, and you're just left with nothing. That's space. But if space is nothing, well, could you differentiate it from, like, not space? And I don't mean just like, well, a rock is not space. It is in space, but it is not space. But, like, could you go out of space? If space is nothing, can you go outside of nothing? Right? What does that even mean? You know what I mean? So it's actually a lot harder of a question than you might think it is. And the thing is, space is not nothing. Okay? Space is not nothing. There are two different main ways of describing space, and it comes down to the two general mathematical models of reality. The first is general relativity. Now, general relativity is, of course, a generalized version of special relativity. Special relativity talks about if you're moving at very fast speeds, how do things behave? General relativity is saying, okay, not just fast speeds, but also accelerations and all that kind of stuff. How does that work? And therefore, how can you build a sort of a framework of the universe? And that's the way of describing space, and that works in terms of on grand scales. Okay, so talking about planets and galaxies and large objects moving through the universe. Gravity is described in general relativity. That's sort of the main whole. If you've heard about gravitational fields and that kind of stuff, that comes from general relativity. So, is described in general relativity. However, there's also another way of describing space and reality, and this is general relativity is sort of top down, right? The biggest stuff, most general stuff, and then going into the specifics from there. You can also do bottom up. So bottom up is, okay, what are the smallest things in the universe, and let's put those together and go up from there. So that is, of course, your subatomic particles, and that gets into quantum mechanics. Okay, so quantum mechanics usually describes it describes how the smallest things in the universe operate. And since everything is ultimately made up of the smallest things, again, it's sort of building it up from there. Now, the problem with these two theories is that they contradict each other. Quantum mechanics is very probabilistic, is very chaotic. There's a lot of kind of random little things happening all the time. But general relativity is it's smooth. It's that here is this large scale look, and it's smooth, it's calm. I mean, sure, you can have chaotic things happen in terms of like collisions and explosions, but in terms of just general movement of things, right? The Earth moves in a calm, orderly fashion through the solar system, through the galaxy, through the universe. Electrons do not move like that. Electrons do not move smoothly. And so that's sort of an issue. And since you can describe space through both of these outlooks, you get two different models. So general relativity describes space as a smooth framework through which everything moves. Actually, let me clarify. Everything moves in a straight line. And you're probably thinking, well, wait, no, it doesn't. Like, the Earth is not moving in a straight line. And you're right. Well, the thing is, it is moving in a straight line. The difference is that space itself curves. As space itself curves. So, and you may have seen sort of images like this. I actually have a GIF for this here. So here you can see the Earth and the Moon, and they're moving around here. So you can see how space is curved, right? You have this normally smooth, kind of featureless platform that objects can move through, and through their mass, through their gravity, they create curves. And so you can see the Moon is moving around in the curve created by the Earth, and the Earth is moving around in the curve created by the Sun. And everything is all smooth and all that works here. Now, this acts like space is two-dimensional, which of course space is not two-dimensional. It's three-dimensional, but it's the same kind of idea, okay? So this is a way of really, think of it like the, what are those things that are like that at like science museums, like the Exploratorium, where you throw a coin down like this thing and it spins all the way around until it gets down in the middle. It's kind of that kind of example. And this is a way of describing space, and it works in terms of large-scale gravitational objects. So this is, it's not like there's anything really wrong with this at all. This works perfectly well. We haven't seen any error of it when we talk about, movement of objects involving gravity and stuff like that. It works totally fine, and this is a totally fair model to think about it. However, quantum mechanics does not say this. Quantum mechanics describes space as a chaotic foam with random particles and energies popping in and out of existence. So here you have your smooth stage where objects can kind of form it around them and move through it, all that kind of stuff. Quantum mechanics is no, it's just kind of a chaotic mess. And quantum foam is often described this way. That literally there's just like pieces that will just kind of bubble up and just poop out a particle, and then that particle will just immediately kind of blip out of existence, and then here's a bit of energy spike out of for no reason, just there's some energy up, it went away. And it's just this completely chaotic kind of seemingly random nature about how this works, and everything is kind of determined by probabilities and wave functions and all this kind of stuff, and it's again, chaotic is the best way to describe it. So these two things are, of course, at odds with each other. You have this, how do you go from this very bubbly, frothy space outlook of space to this very smooth stage outlook of space? And this is a legitimate problem. If you try to apply quantum mechanics to quantum mechanics to, like, Earth and gravity and stuff like that, it doesn't work. If you try to apply general relativity to quarks and electrons, it doesn't work either. So you have this weird thing where you have two theories that are right in their own environments, but if you try to put them together, they just don't agree with each other. And this is one of the biggest issues with physics right now, is that we have these two theories that are absolutely, as far as we know, as far as we can tell, they're totally correct about everything in their framework. But if you try to combine them or try to swap them around, they completely break apart. But there is only one reality, right? So how do we deal with this? And sort of combining quantum mechanics and general relativity is one of the big issues that people are trying to work with. And this is also when I talked about bosons, about how, like, the graviton is not really a thing exactly. This is sort of why, right? Like, quantum mechanics says there should be this particle called a graviton, but general relativity says, like, no, you just need to curve space around, right? And we don't have a good answer for that. So yeah, this is where things get to be very complicated. But the key with all of this is that space is not nothing. There is some sort of structure, and there is some sort of inherent energy. So this is true for both of them. There is an inherent energy to space. And this, if you've heard of this, is called dark energy. Now, we don't really know anything about dark energy. We don't really know exactly even if it is an energy, or if it's just like some sort of, or what it is, really. It's not energy in the sense of like, oh, you can use it to power a light bulb. Like, we don't think that's what it is, right? But it's some inherent quality of space where it's not nothing. And this energy is actually what is causing space to expand. Okay? Is causing space to expand. So again, it's the whole like expansion of the universe, and we'll get into this a little bit more later next week. We have this expansion of space, and in fact, right now, if you look at everything in the universe, we have matter, we have energy. There's also dark matter, which is basically just it. We call it dark matter because basically we need more gravity than there is for like galaxies to even exist, basically. And so we say, okay, there must be some stuff out there that we cannot see, hence it's dark, but it has mass, it has gravity, hence why it's matter. So there's those things. Those are all in space. But then space itself has this sort of dark energy. If you were to kind of combine all of those together and look at sort of like how much energy in total actually is in the universe, dark energy is like 70% of the universe. So the energy of empty space is like 70% of all stuff in the universe. So in other words, it's like twice as much actual energy than like everything in the universe. And so the fact that our universe is actually dominated by this dark energy is what is actually causing the universe to accelerate in its expansion. And again, I'll cover this more a little bit next week. And in fact, accelerate at the moment in its expansion. Anyway, we'll talk about expansion of space and sort of that kind of stuff later. But just remember that there is an inherent energy to space. And in other words, there is something there. And there is some sort of structure. Now, it's kind of hard to describe a structure in this sense because when you think structure, you think like, you know, either you see like the stage kind of idea here, which is this is a two-dimensional thing, right? So, well, space is clearly not two-dimensional. But if it is three-dimensional, you think of it, okay, well, there must be some sort of difference, right? And it doesn't really seem like there is a difference, right? If I keep going in one direction, space just kind of looks the same, where if I go in another direction. So it's like, well, how is there a structure if it's all just the same? But the idea is, again, it's this sort of framework, and that you could get out of the structure. And what does that even mean? So here's the thing. This universe, you can see right here, as this is modeled, space here is two-dimensional. Now, it's being curved in a third dimension, right? The sun is causing the two-dimensional space to bend downward into a third dimension. And this is kind of where we get to something that's more complicated. So I actually want to talk about what do we mean by dimensions? What's the idea with that? Let's start down with zero dimension. What does a zeroth dimension look like? A zeroth dimension is one where you can't. There are zero ways to move. Okay, so what would that look like? A point. A point is a zero-dimensional object. Okay, it's there. You can't go one way or the other way. It's just you are there. A one-dimensional object is one that where you can go one way, and when I mean one way, I mean also forwards and backwards. Okay, so a one dimension is a line. Okay, so let me actually kind of go about this. So let's talk about dimensions for a second. So a zero dimension is a point. You can't go in any direction. Okay, so one dimension, a line. You can go in one direction, say forward and backwards. Forward and backward. Okay. Two dimensions means now you can go in two different directions. So this would be a plane. Okay. You can either go forward or backward, or you can go, I'll say left or right. Okay. And go in two directions. Forward plus backward, left plus right. Okay, We'll just say left and right as an example. So in this example here, think about like so a piece of paper, right, is two-dimensional, right? I can move my pencil forward to backward, left to right, and I could do any sort of combination of that in terms of weird squiggles or curlies or whatever. But that's kind of it. So in other words, think of it in terms of like if I'm graphing this, right? For a point, how many different numbers do I need to describe where I am on the point? Well, I don't need any. I'm just on the point, right? A line, I need one number to describe where I am on the point, right? Think a number line, right? In a plane, I need two numbers, the whole Cartesian coordinates, right? X coordinate, Y coordinate. I need three numbers to describe where I am. So 3 dimensions is, I'm going to say, a volume. Basically, you can go in 3 directions. You can go forward, backward, left, right, and up or down. That's not useful down. Okay. So here now you have, again, an actual volume. I don't want to say the word space because that's kind of its own thing, but you have a volume. You can go up or down, left or right, forward or backward, or any combination of that. You need 3 different numbers to describe where you are, right? The X, Y, and Z coordinate, right? Now, also what you can do with this is kind of think about how each direction that I'm adding is perpendicular to the previous ones, right? So think about, you start a line, okay? If you start with a point. Well, okay, let's start with the point. You start with the point. How do you get a line? You basically stretch the point in a direction. Okay, so here, let me actually use paint to kind of draw this out. I'm going to go a little bit fancier and use GIMP here. Use some fancy image editing software, basically just free ghetto version of Photoshop, but whatever. Come on, don't take forever to load. All right, here we go. Okay, so let's just do standard whatever. Yeah, sure. Okay. So I want the... No, I can't find the tool I want. I guess I could just use the paint. Well, this is all what you all wanted to see, I'm sure, right? Okay, yeah, let's screw up, use the brush. Okay, so that's a big, okay. I don't want it to be that thick. I'll have the size go down to 5. Okay. Okay, so that's your point, right? So that's your 0-dimensional space, and there you go. So now, oh, there we go. Okay, so now to get a 1-dimensional object, I basically want to stretch it out. So say, okay, let's stretch it out to... Why did that not? Oh, because I thinged. Hold on. There. So there's my line, okay? I've stretched it out, and I get what I get in that sense. Okay, now the idea from here, to get to a 2-dimensional thing, is I want to take this, and I want to now stretch it out perpendicular to the way I stretched it before. So now, I'm going to stretch it perpendicular to the way I stretched it before, okay? And now, I can connect these. And together. Okay, and now I have a 2-dimensional object. Okay. So now, how have I done this? I stretched the 0-dimensional object to the left and right. Then I stretched the 1-dimensional object up or down. So now, to get a 3-dimensional object from this, what I need to do is... That's not what I want to do. Is I want to stretch this forward and backward. I need to stretch this perpendicular to how I've stretched it before. Now I can't really do that showing here, but I can kind of do some perspective, right? So now I can kind of do this. And now I can connect it. Whoop, that's not what I wanted. Again, it's not going to be perfect, but you can see the idea across. And so now I have my 3-dimensional object. Okay, my 3-dimensional object. So here's the thing, I could theoretically keep going. If I could somehow take this whole thing, and stretch it in a direction that's perpendicular to any other direction, what would that? I would therefore create a fourth-dimensional object. Now, I can't do this in a way that makes any sense to our brains. Okay. However, I've kind of already tricked you, because if you think about it, this is not a three-dimensional image, right? It's not. This is a two-dimensional image because it's a two-dimensional screen. So, but I've tricked you because I basically sort of emulated what a three-dimensional object looks like in a two-dimensional environment. So similarly, you could kind of do a similar thing if I had this in 3 dimensions. And I don't, so I can't exactly show this to you. But you could sort of trick your mind, if you do have an actual 3-dimensional object in front of you, to sort of think about what a 4th-dimensional object could look like. And one way to do this is, there's a couple ways to do this. One of them is to sort of take the whole thing and sort of extrude it like within itself. Wait, hold on. Okay, now. Sort of scale it inward. I'm gonna keep going. And so you may have kind of seen this image made before in some manner. Something like this. And so this would be the description of, and then I have to connect to all of these points again. This goes to this one. That one. That one's kind of already, perspective-wise, is already fine. Well, still. It's something like this, right? You may have seen this before as something that's called a hypercube. So this is sort of a way of describing it. It isn't a cube because it's not all sides are equal, but this is a way of kind of describing this. So let me actually kind of Google this. You can see an image for this. So hypercube. Yes, hypercube. Yeah. So you've seen this kind of image before about how like a cube inside of a cube. So that thing's neat. Yeah, I've seen this as like this is like a one-way mirror with LEDs inside of it. It looks really cool. But anyway, so there's a lot you can get from this, and so here's a weird example. And there's other ways you can go about this. But this is sort of a way of sort of theorizing a sort of theoretical fourth-dimensional object. But this doesn't really make any sense, because the way to think of it is you've gone in a direction that is perpendicular from all previous directions. And again, our minds are in 3 dimensions, so trying to imagine what this looks like higher dimensions doesn't work. It just doesn't work in our heads. Actually, wait, is this an idea? Is this like a GIF we can see for this? Because this actually is kind of interesting. Folding a hypercube. Okay, not what I wanted, but there is a way of folding this that actually is like help describe this a lot. I think nothing's loading right. There is, I'll see if I can find a video and I'll link this in the notes to maybe kind of get into this a little bit more. Yeah, so anyway, the point that I'm trying to say is that you can go further than this. So 4 dimensions is also say a hypervolume. You can go in 4 directions. And we don't know what that, and again, we don't know what that fourth one would be called, what it would look like, or whatever. And again, here's the thing, you could keep going. You could theoretically keep going as long as you could find other perpendicular directions to go to. You can theoretically keep going forever. Now, you may think, what's the point of this? This all seems super abstract and theoretical, who cares? It is actually can be kind of helpful, because remember how I said that, like, 2 dimensions, you can describe your position from 2 different points. 3 dimensions, you can describe your position in 3 different points. So you could sort of use 4th dimensional as an analogy if you are trying to describe a data set that involves 4 different variables, right? Then it can kind of help you sort of in terms of like how this could work, and you could keep going from there. But even besides that, you can do like multi-dimensional math like without any extra whatever. You don't need it. In in physics, there actually are ideas. For example, string theory, which says that like you actually do need these like higher dimensions of space to like do things. And so that of course gets super abstract and weird and nobody really knows what it's talking about. But my point is that let's go back to this image here. Here you have a two-dimensional universe in this image that's being bent by objects in this third dimension. So the idea is, what if you could go further? What if you had an actual three-dimensional universe that you could somehow bend, or in other words, you could maybe move in a fourth dimension that's sort of out of the universe? And so this gets back to the warm-up question. The warm-up question was, can you go faster than the speed of light? And the answer was not through space. But space is three-dimensional, as far as we understand it. So if you could somehow move out of space in a fourth dimension, theoretically you could go as fast as you want. Now this is the basis behind a wormhole. So here is an example, a two-dimensional example of a wormhole. You have a two-dimensional universe, right? You have this flat sort of universe. And the idea is you have basically come out of the universe, out of the piece of paper, and you've just sort of moved through three-dimensional space back into the piece of paper. And this is something that's totally theoretically possible. One idea for this is that this is what black holes are. That black holes are basically, they're sort of rips out of the piece of paper that is the universe, right? And they kind of can connect to another part of the universe. This is something that is, of course, very, very, very theoretical and not anything confirmed in any way, but it's possible. It's totally possible that this could exist. And instead of having to go all the way around through this piece of paper to get to where you want to go, you could just pop out, pop back in, and there you go. It'd be easy. Now, how you could create this and how you could deal with this, nobody really knows. So that's something we could get in that sense. So let me actually kind of write this in. So theoretically, you could move out of space and then come back in at another position without having to move all the way through the universe. This is a wormhole. Okay. So that's one way to sort of cheat the system and, in a sense, move faster than the speed of light, because, for example, again, in this example here, if you're moving at the speed of light, you would take 25 years to get to the star Vega, but I'm sure if you just went for boop doop, it would not take 25 years. I mean, theoretically, if you lined this up perfectly, it would be instantaneous. So, in a sense, you've moved faster than the speed of light in that sense there. However, something else you could do, thing you could theoretically do to move faster than the speed of light is to move space itself. Space is a thing. It has an energy. It has a structure. So if you could actually somehow move space, and then, in a sense, because again, the idea is you can't move faster than light through space. But if you could just move space itself, well, you could move space itself however fast you wanted. So, in that sense, for example, think of it as not this line, but what if I sort of stretch this out, so I have Earth to Vega, but then I just took the piece of paper and I just kind of scrunched it up. And in that case, well then, I could just kind of really easily just walk from Earth to Vega, just boop right there, because my distance has been squished way inward, right? Now, how you would do this is, of course, who freaking knows. But there is actually one idea that actually could be related to gravity. Because if you think about it, what is this idea of general relativity in terms of gravity is this sort of bending of space. So if you could somehow, super duper bend space to the point where, Earth to Vega is all just, in this one, divot right there, and you could just sort of get right across from the other, that is a possibility. Now, of course, the question is, well, what would happen then to, if there was, another planet, in between you? How would that work? Who knows? Nobody has any idea. But this is all, incredibly theoretical. But it's theoretically possible that this is a way to get this to work. So think of it as basically you're treating space as a moving sidewalk, right? And you have a top speed while you are, running across, the ground, right? You can only run so fast. But if you get onto a moving sidewalk, you can therefore end up moving faster than that. And if anything, your limit is as fast as the speed of the moving sidewalk. right? So that's the idea of this here, is that you theoretically could move faster than the speed of light if you could somehow move space itself. I think that and again, this is just a purely think idea, that this is sort of the key in terms of like moving in terms of like an interstellar civilization is some way, because again, speed of light is too slow. The speed of light is too slow. We would need a way to move faster than the speed of light, and either this sense of wormholes kind of popping out of space then popping back in, or scrunching space up and just kind of jumping the gap. I think that's the one of those is something that we kind of have to do in order to get anything in. How do we actually do that? Good question, but it's at least an idea. Now, however, if we're talking about popping out of space, then the question is, well, then what are we popping into, right? And of course, then the next idea is, well, if we pop out of our universe, could we pop into another universe? So this gets to the idea of the multiverse. So the multiverse sounds like a very nice, kind of fantasy science fiction comic book kind of, oh yeah, sure, multiple realities, yeah, sure, totally. But there is a basis that this is sort of kind of maybe is possible, sort of. So the multiverse is the collection of all individual universes. Now, there are several kind of models for what the multiverse could even be. And also, it could just not even exist, right? Maybe there is just our universe and that's just it. That's totally possible. But one of the ideas is kind of like, well, if there's one, why not more? Right? Well, why? So I'm going to give you some ideas, and this does not cover all ideas, but there's a couple of them. So here are some ideas for a multiverse. Okay, so the first idea is multiple 3D universes in one 3D reality. Okay, here's what I mean by this. And of course, I'm going to be drawing this in 2 dimensions because I'm lazy, but yeah, so let me just delete this. Okay. So let's say we have here is our actually I don't want to circle it. So here's our universe. Let's say, there's a galaxy. Ooh, look at this galaxy. It's great. And then here's another kind of galaxy. Woohoo. Obviously, the scale here is really off. And then here's another thing. It's a spiral, whatever. Okay, so here's a universe, all right? It's over here. Here's our universe, and we're doing our thing, and, all this stuff. And, for example, the size of the observable universe is basically how big of an area do we actually see staring out into the universe. And there is a limit to that based off of how old the universe is and how it's growing, because we can only see as far back as, or we can only see as far as to the point where light has been able to reach us in the age of the universe. So, for example, if we're here, let's say we could only maybe see out to here or so, in a circle. But that doesn't mean there isn't more stuff out beyond that. So let's, that could be a possibility, whatever. But this is our universe. It's growing, it's changing, it's doing its own thing. Okay, cool. However, and this size of our observable universe is, I think it's like 93 billion light years across. But let's say the entire universe is even like 10 times. Let's say the entire universe is 1 trillion light years across. Okay, let's just say that. I'm making that number up. I have no idea. But let's say that's what it is. Well, it's totally possible that 100 trillion light years over here, there's just another universe. Doing its thing. There's just another one over there. And maybe there's another one over here. That doesn't look right. That also looks terrible. What am I doing? I don't know what I'm doing. It's a galaxy, I guess. I don't know, whatever. This is another universe over here, okay? And you get all this great stuff. So the idea is that there could just be other if we just kept going forever in one direction, and again, we'd have to be able to break out of the speed of light to even get anywhere, because again, each of our universes are expanding, right? At least our universe is expanding, so we'd have to somehow go faster than the expansion of the universe, which good luck with that. But theoretically, if you kept going forever, at like an info, like an, basically as fast as you'd want, you could eventually just run into another universe by just driving forever, right? So that's a possibility. The idea is that the time scales and the distances here are so large that like it's not really going to matter. I mean, theoretically, I guess like our universe could grow into this one or whatever, but like it's such a giant distance and a giant time that that's basically not really a thing that's going to happen. This is an idea. Now, what's convenient about this idea is that like physics should probably be the same because physics is governed by reality. So you would have basically multiple universes existing apart from each other, but you could theoretically just head out in one direction and get to another universe. So distances would be so large, this would be basically impossible. So this is one thing that's a possibility. Another option, though, is again the whole idea going back to a wormhole. Is that, well, maybe instead of popping out of our universe and then popping back into another place, what if we just pop into another universe? So the best way to kind of, and this is basically multiple 3D universes next to each other in one 4D reality. Okay, so the best way to think about this is think about like a bunch of sheets of paper stacked right on top of each other. Okay, now I can make drawings and landscapes or whatever on each of those pieces of paper. When I stack them on top of each other, those, they don't interact with each other, right? If I were to draw a person in the woods on one piece of paper and then draw an ocean in another piece of paper and stack them on top of each other, it's not like the person in the woods falls into the ocean, right? That doesn't happen, right? Because they're separate. But the idea is if you could somehow break out of your own piece of paper, your own universe, you could kind of go back into another universe that's sort of next to you. And again, it's perpendicular to you in this other direction, in this fourth dimensional direction, whatever that direction even is. So this is kind of one idea for how this could work. So you would have multiple 3D universes existing side by side with each other in a larger 4D space, like sheets of paper stacked on top of each other. Now, with here, since each universe is kind of its own separate reality, you can have all of them have just different laws of physics. So that's interesting, and how that would even work. Nobody knows what even different physics would even mean. But, maybe for the force of gravity, instead of GMM over R squared, it's suddenly GMM over R cubed. Maybe that's just how it is. Or maybe G is 10 times stronger, 10 times bigger. Maybe an electron is the size of a basketball. You know what I mean? Like, who knows, right? So, that's just kind of how this stuff could work, and we'd have no idea how this would be. And that could be a problem, whereas, for example, hey, I'm going to pop out of my universe and pop into this other one, but if the other one just has laws of physics that are just not conducive to my existence, then you would just like immediately die. So, or you immediately stop existing, which is even better, I guess. Black holes and wormholes, again, ideas come from this. One idea is that black holes sort of can feed into other universes. In this sense, they sort of break out of our pieces of paper and go into the next one, right? Another idea that kind of leads off of this is that black holes actually create to the births of new universes. So that's another idea that sounds kind of nice, but again, we don't know. And yeah, that's something that you could kind of get to that's kind of trippy about this kind of stuff. But there's another option that's even more trippy. And this other option is described as called the many worlds interpretation of quantum mechanics. So quantum mechanics, again, everything is based off of probabilities, right? Think about, the whole thing of, has the atom decayed or has it not, right? Is Schrodinger's cat alive or dead, right? That kind of stuff. And the idea is that, well, the fact that we get, even though it's a probability of something that's to happen, a thing is going to happen, right? The atom will decay or it won't. It's just one of those will happen. We just don't know which one yet until we look at it. So one of these ideas is a way of thinking of it is that, well, actually, in any situation, all possibilities happen. It's just that we end up in the reality where the one that happens is the one that we see. So in other words, whenever there is a choice, all possibilities happen in their own universes. Okay, so this is kind of the whole idea about like, you know, oh, like alternate history kind of stuff, where like people talk about like, oh, in this universe, like, you know, the South won the Civil War, or you know, Hitler got into art school and didn't kill everybody, you know, or whatever, right? And that kind of gets this whole idea of this, and this is very much like really opens things up into like how this even works, and then okay, how do you go from one universe to the other, and this is the thing. But this is a legitimate scientific theory that this could be real, so that's the thing to think about as well. So we have no um, we have no evidence that like any of this actually exists, right? We have no evidence that there's a multiverse, that the multiverse is real. It could be totally all just not real and just science fiction, and who knows. But there is at least basis that it could be possible. So that's something that's interesting. And there are a couple things that are odd. The main one that I've heard of is something called dark flow. Um, and the idea for this is that if you sort of look in the sky and like if you think about the universe, the universe would be roughly homogeneous. So what this means is that if you take it's sort of like homogeneous basically means if you take a random sample from the bigger thing, it's going to look kind of the same as every other random sample. Okay, for example, the ocean. Right? You take a random glass of water out of the ocean, you take a second glass of water randomly out of the ocean, they're probably kind of the same. There's water, there's probably some similar, you know, plankton in them or something maybe, or, you know, similar, different, like, maybe there's like a little bit of salt, no, there's salt of course in them, but there's other, maybe some elements in there as well, but they're pretty similar. So the idea is if you were to sort of scoop up some part of the universe and then scoop up another part of the universe, they would kind of look the same. Okay? Except there seems to be this region of space where galaxies seem to kind of be like moving in a specific direction. And nobody really knows why. And so one of the ideas is that like there's another universe over there that's like pulling on us through gravity, which is weird to think about. That's not like the the simplest explanation, but it is an explanation, so that's kind of interesting. And there's other ideas too, of course. There's the idea about like, well, you know, why would our universe be the one that exists? Why are we special? Why is it just that, you know, why it's kind of presumptive to think this, we are the one universe. Why wouldn't there be multiple of them and all that stuff? There's also the whole idea about, oh, the universe is a simulation, which like, I don't want to get into that because honestly, it's just not really an interesting conversation because like, okay, so what? Right? Like if the universe is a simulation, okay, what are we going to do about it? Right? Like, you know, who cares? So yeah. This stuff is really bleeding like the lines between like science and philosophy because it's like science means you have to be able to like test for it and prove things, and we kind of can't do that with this. So you know, maybe at one point we can, but at this point, no. Oh, one thing I kind of forgot to mention about wormholes, I want to get into is so when you talk about wormholes, basically a way of connecting different points in space. You could theoretically also use a wormhole to connect different points in time. So in a sense, you could create like a time hole. Okay, so like, you know, think like you create a wormhole and you've anchored one point in like, let's say you've created the wormhole in like, I don't know, year 2100, and then you kind of leave one end there, and then you just take the other end with you as you move through, you know, your life or whatever, and then anchor it in like 2150. Then if you go into the one in 2150, you'd pop back out in 2100. That's the theoretical idea of way of thinking about it. Of course, then it gets to the whole idea about time paradoxes involving time travel and like, you know, the whole thing about like, you know, you like kill your dad before, you know, you're born, and like how does that work, right? So there's stuff like that. One of the ideas is that like the easiest idea for me in terms of like time travel back to the past. Well, there's two main ideas for time travel back to the past. One of them is that you can't interact with anything, and it's almost like sort of like watching a movie. You know what I mean? It's like you're just seeing like, oh, I can see everything and I can know what's going on, but I can't actually like actively affect anything. I can't change anything. The other idea is that, well, when you're time traveling, you can actually just go into you end up either go into or you end up turning your universe into a parallel universe, right? So whatever has affected, you can't go back in time into your own universe. You just go into a different universe and kind of affected that way, or by changing something in the past, you've sort of already split the timeline or whatever. And again, this sounds very comic booky, but that's kind of an idea. There's one thing that I actually heard is interesting, and this is again totally very fake kind of fictiony writing, but I kind of like the idea. Is that like um, you can't time travel, but if you go into a different parallel universe, maybe they're just kind of offset in time. So the way I think of it is the way I describe it was like time zones, where if right now I'm in, it's I don't know noon in California, but it's 4 o'clock in or it'd be 3 o'clock in New York City, right? So the idea is like you could have like a parallel universe where it's 3 o'clock now, but if I go into this other universe next to me, it's 12 o'clock, right? So like that's kind of a neat idea, but like again, that's completely fiction. There's no idea if that's real. But it's stuff you can think about, and it's stuff that's very trippy and very weird. Um, all of this stuff is very trippy and weird and hard to think about. But I think it's kind of interesting to talk about, interesting to think about. Um, and you could definitely get into kind of weird stuff with that. So I want to see. I think I want to find that video that talks about like higher dimensional shapes and see if I can plug that in. I don't know. I'll see if it's actually worthy or not. But yeah, I just kind of want to talk about this stuff, and I think it's interesting. And I don't know. Of course, if you want to delve into this, there's a giant rabbit hole that you could go into. So yeah, if you want to, you can. But yeah. So yeah, so Monday, I'm gonna be a Kahoot. There will be a. I'll be going over the worksheet. Tuesday, I'm gonna have a video on sort of the history of the universe. So going back to the birth of the universe, kind of what's changed as we go along, and then also going into the future of the universe. Also, Tuesday, I will be linking a video on YouTube, which might be the best video on YouTube I've ever seen, which is a lot of praise to give, but it's an extremely well done video on the future of the universe, and I really want to share that with you because it's an extremely good video. Yeah, and then after that, kind of done. With the unit and also with like the year really. So then, I'm gonna put together some review videos, and with those review videos, then you will have that, and then you will be given the final. Um, the final will be the same kind of format as the electricity test. Um, it will be 8 questions in total, but they're not quite as long as each individual question on the electricity test. So it's the same kind of thing as the first semester final. It'll cover again 2 questions for each of the 4 units of this semester. And you will have, the formula sheet and stuff like that. And you will have like over a week to work on it. So, yeah, you'll have over a week to work on it, and you can of course work with each other. That's totally fine. That's the purpose of it. The second semester final, because the whole fact about like seniors graduating early or whatever, I've actually had it like as like a kind of take home work on it together final before anyway. So that's kind of what to expect for that and how that's going to go. So, but again, you'll be getting that. I'm not sure if I want to give you the final next week Friday or the week after that, but we'll see. So yeah, but we're almost done. So that's kind of crazy to think about. But anyway, before we fully finish everything, you have a rapid question. So describe in your own words what a wormhole is and how one would use one of them. Because describing in your own words, I'm actually not going to give you an answer for this. So you're just going to have to fill it out and kind of do a conclusion on your own with that. Write a couple sentences describing it and how it works. If you want to look it up again and kind of get some more information what other people say, and you can do that as well. Don't like turn this into an essay or anything, but don't just write like 5 words. So, yeah, we're approaching the end. So, oh boy.